Okay, so thanks for doing this accommodation for me. I know that the workshops are supposed to be in person, but I couldn't be there. I wanted to be there, but this is completely out of my control. So I appreciate it. I'm gonna start by acknowledging my collaborators in all of this work. Kathy, who you know, she's been instrumental in at least in the first part of this talk. Andrea Morad, Min Hudiao at the San Francisco State University, Daniel McCoy at the University of Wyoming, and a lot of the group, a lot of their students, they also collaborated with me in doing this. So let me see. There it is. So, well, someone said yesterday that I was presenting these nice visuals, animations. Well, we also have nice animations at NASA. I'm presenting this one. I don't know if you have seen it before. Um, this is from our 5 kilometer resolution simulation. This is from actually a few years ago. Bill Putman, who is the lead of this project of the whole GML modeling initiative, he puts together this kind of animations and this kind of simulations, and I really love them because they show all the things that we're trying to understand here. In white, you can see all the cloud fields, and in here in color, you see the aerosol fields, and you can tell, there are large scale features. That cyclonic activity. You can see maybe even the Rossby waves. You really pay attention. Um, you see the diurnal cycle, but also you see this small scale, features, convection popping up here and there, small scale, clouds and small cumulus. So, and all of that is, put adds uncertainty to all of this and complexity to the things that we're trying to do. Let me see. Here, there it is. So, if we think about how models work, different models, they aim to represent different scales. And also because because different processes they act on different scales, and we know this. So it could be from seconds to minutes, like turbulence, or years, decades, or to centuries if we're talking about long-term climate change, right? And at the same time, we have a small, if we want to represent this, we need to be able to resolve that. We need a very high resolution model, right? Or if we want to represent large scale climate change, then we need probably a lower resolution model, like the hundreds of kilometers grid scale. If we come down this ladder, then we have like 5 models for analysis of probably around the 150 kilometers seasonal to subseasonal to seasonal water numerical weather prediction, and this is the new class of models. Well, other simulations that actually pop up like 10 years ago. Global scale storm resolving models, global cloud resolving models, and then LDS. Thing about this is that we can really focus on one process, but the reality is that all the processes at all scales that are interacting all the time, right? So when we go over here, in this direction in this plot, then we gain domain coverage. We go from centimeters all the way to global, but then what we start having is a lot of limitations on how we resolve the subgrid scale variability. So how do we go about trying to account for those things? Well, we got data, and that's why we are at NASA, the GMO office, we are most interested in trying to come up with data, observation-based modeling. But that's what we do. We do observations and try to put that in context. So over the last few decades, there has been a lot of atmospheric data collection, and you know this too. I counted really about 100 field campaigns starting since 1980. That could be, well, that's had in NASA, NSF, DOE, AOP, it could be this AOP type or the airborne. So there are a lot of data floating around. Also, we have long-term ground-based observations stations around the world that have been collecting data and on clouds or other things for a long time, 10, 20 years, some of them even go back in like a few decades. And of course, we have extensive satellite retrievals. That's probably some of them. This is probably you can see this, but this is the A-Train. That was a very successful mission or number collection of satellites, collection of platforms that were flew for a long time, and they produce a lot of data that is currently still used in the field. Over the last 2 years, let's say 10 or 12 years, there has been this explosion also in computing power, and we also have these high-resolution global simulations, which are typically called global cloud resolving models or global storage resolving models. And one very well-known project is the Diamond project, and some of these simulations go all the way up to 1 kilometer. This is also something where we, the GMO, at NASA, have been involved in under the direction of Bill Putman, and our model is actually right here. And this is the same simulation that, well, actually, this is our updated simulation from the one that I presented at the beginning. So, and this is also data. These simulations are not supposed to be operational. They are more like experiments where we can learn about subgrid scale variability and other things. But really, they are not supposed to go beyond a few weeks, although actually we have one that goes a few years, but that's not typical. Well, this is just to emphasize what we do at the offices. As I mentioned before, we do have those kind of simulations and different. He puts together these kind of simulations, and they produce a lot of data. Some of them actually go all the way up to 1.5 kilometers in the global, and they include chemistry. Some of them are coupled. Some of them include aerosol. Some of them include aerosol cloud interactions. So we actually have a lot of data, and this is actually open to everybody. You can download this kind of data sets from the NASA website. And on the other hand, we also have reanalysis, right? They are lower resolution on the order of 50 kilometers to 100 kilometers. You are all familiar with it because almost all foundation models are trained on these things. And they represent, of course, the best estimate of the multi-decadal climate. They usually start from 1980, era 5, I think that you can go all the way back to 1940. Some of them are less constrained, but you can actually go out all the way back to probably 1900s. Maybe we actually use one in this talk. And the nice thing is that they assimilate a wealth of observations using conventional data assimilation techniques. So we have that represent a baseline from which we can start building, and that's actually very nice. And again, to try to advertise a little bit more, we at the GML put out a product which is called MERA2. That's where when MERA2 is developed, and that probably you're all familiar with. That is like the one of the major reanalysis along with era 5 and others. So that's kind of the major context that I want to start with here. If you think about how we develop new parameterizations or new data and new schemes in a GCM and a model, well, typically, I put this together. I don't know, it's not supposed to be all encompassing. It's just, a way to think about things. So we have lab data, or new theory, field data, and then, we come up with a new parameterization that is implemented in a model eventually. And then on the other hand, we can have these instrument measurements, airborne or spacecraft. And then some other group has an algorithm based on simplified physics. Then that is validated on field data, and then eventually versioning like L1, L2, L3, that kind of things. And there, the modelers like myself, we take that data and then we test it, right? That's our new parameterization. If it works well, then okay, nice. But usually it doesn't work well. So you have to feedback and go and retune the model and try to make it work and make it look more similar to what the algorithm is saying. Now, of course, on the other hand, on this branch here, there is algorithm versioning. So there is a new data sets that are improving in this or that thing, depending on what observations they have or what new technologies come about. So this is like very historically how it has been done. That is the current paradigm, how we develop GCMs, right? And it's also, I'll say this, how we typically train natural neural networks, also known as grad students, right? This is how we all know how to do this, right? I'll say that, well, recently we can probably, this loop here can be kind of shortcut by using AI, then we can go directly from the data to the new parameterization. But still, I will argue that the new parameterization is always evaluated as a part of a full model. So it's not just, we're not evaluating the process itself, right? We're evaluating how this parameterization works in the GCM. And that's a problem because the GCM has a zillion parameterizations, right? So there are many compensating errors, many things that are going on at once. Also, the retrievals, they don't take advantage of all the physics that we develop here, but essentially they develop their own physics to come up with these algorithms and these retrievals. And this is, of course, a very slow process from the development of a new theory to when it becomes operational in a system. It can take 20 years, really. It's really slow. So what we're trying to do here is, okay, maybe we should just throw all the data in and come up with new models and new products that are using AI, leveraging AI for that. That synthesize all the experimental observations that we have. It could be satellite, aircraft, ground-based. On the other hand, also uses the model simulations that could be multi-scale, long-term reanalysis to inform those retrievals. And so we can, we're interested in some target Y in this case, then we can model as a function of a state and get that distribution, of course, and then at the same time obtaining the parameterization and the retrieval. So the two things at the same time. And that could be an advantage over the segmented approach that I presented before. Of course, it will work better for derived quantities for which we don't really have an observational estimate, like, for example, cloud microphysical variables, so that we don't have a good observational estimate, I should say. And the only caveat is that it still requires a conventional modeling, but the retrieval could use that conventional modeling to improve the product. So of course, the question here is, how do we actually go about doing this, right? What is that, And there are ways to do it. And this is not the best one, but it's just one way to approach it. And that's how we've been approaching this at NASA. Well, just two steps. Just train a model and refine on observations. That's typically how we will approach this kind of thing, right? So let's say that we have pairs of data, a simulated X, and we have also a simulated target, simulated state and a simulated target. Then we're trying to connect those two things. Then we can just train one thing into one neural network to just connect those things, those two things. That's actually not a very hard problem to do. Then we have observations that can be episodic. There could be some observations that are independent of this, and then we can take that observations and this prior NN, we freeze that one, we freeze that first neural network, and then we add a correction head that will correct whatever problems or whatever shortcomings are in this theoretical approach to get something that is closer to the observations. This is kind of a glorified or too complex a way to explain transfer learning, but it's really not transfer learning, and I will tell you why later. So that X can be satellite retrievals, can be reanalysis data, can be field data, and the Y could be cloud variables, aerosol composition, wind. So this is in principle a simple scheme. There is nothing revolutionary about it. Problem is that it becomes complex really quickly. Well, why? Because we have unresolved subgrid variability, we have observational errors in box X and Y. We have limited observational coverage. And we know that every time that we have an experiment, that probably will have very limited domain. And it's not typically nice data. It's very full of nans and missing data, and we have to account for that somehow. And there is a mismatch typically between the domain of the observations and the domain of the model. So that's kind of the context, the introduction that I want to give here, and why, how we're going doing this. And I'm going to go a little bit more in detail on a specific variable that we are interested in. And that's because I'm a cloud physicist. So we're interested in cloud variables right here. To kind of give you, I'm not going to go deep into the fundamentals of the cloud physics here. I'm just going to give you a tutorial of, a very short explanation of why we are interested in these variables, and then kind of stick to the machine learning part of this. So if you think how we model in a GCM, a cloud formation in a GCM or any atmospheric model, typically goes like this. We have aerosols hanging around, they're minding their own business. Then there comes this buoyancy, this forcing, and they lift them up, with some vertical velocity that we call W, right? Eventually, that produces supersaturation. Those guys start to grow, and then eventually there is an uncontrollable growth. They go beyond their equilibrium state, and then grow like 10 times their size, 100 times their size, and then become cloud droplets. This is a very oversimplified way to think about this, but it works for this presentation. Of course, there is a lot of things going on, aerosol properties, how this will be distributed. There is ice eventually, just keep going. So, but for now, this is okay. So in the next few slides, I'm gonna try to explain or try to detail how we go about implementing that scheme that I just showed before for two variables that are of interest in this particular scheme. The first one we call WNet is try it's a constraint neural network to estimate these variables, the vertical velocity at the scale of the individual parcel. And the second part of the talk will talk about cloud droplets, the cloud droplet number concentration that we use to see or to test whether this is a good model or not. I should have mentioned that now that I see it up there, that of course, having this right is very important for us because there is a major uncertainty in weather and climate predictions related to how clouds are formed and how they evolve, and you know that too. So, oh, there was an animation there. So vertical wind and cloud formation. Hold on. So as I mentioned just now, air vertical motion drives the formation of cloud droplets and ice crystals, right? So again, you have the aerosol, it gets lifted, and then eventually it goes into droplets, right? The thing about this is that the scale of this parcel is meters, probably between 100 and 1,000 meters. And our grid cell is something between, depending on the model that you're talking about, between 25 and 100 kilometers. So if we assume that the distribution or that the aerosol is almost homogeneous within that 25 kilometers, which is kind of an iffy assumption, but we still do it, then that cloud formation rates are essentially determined, or the distribution of cloud formation rates within the grid cell is determined by that distribution of vertical velocities. Since the dynamics itself, if you have a non-hydrostatic model, is able to resolve the mean of that, then we are mostly interested in that width of the distribution. And I'll be calling sigma W. That's the standard deviation in vertical velocity. Using that, we can actually get the grid average cloud droplet formation rate, which is what we are interested in. So what data sources do we have to constrain this kind of problem? Well, from our own work at NASA, at GMO, well, we have these explicit kilometer scale models that are able to resolve some of this variability, because we can for each grid cell, let's say a 25 kilometer grid cell, there is a distribution, or we can get a high, well, let's say between 64 and 256 values of vertical velocity if we can resolve that directly into the GCM, into this high resolution simulation, the global storm resolving models. As I mentioned before, this is physically based. We like it because it's based on the dynamics of the model. It's global, which is nice, but it's also very expensive. So it's not something that we can just do every time that we need this variable. Biases, there are studies showing that that they actually are better at representing microphysics and dynamics, but they are still not perfect. There are still biases associated with this model, right? And of course, it can resolve all scales. It doesn't matter how high you go in your resolution. There is always a component of the variability of vertical velocity that is going to go unresolved. On the other hand, we have observational data, W and the sigma W. They can be retrieved using Doppler, radar, and LiDAR, mostly from the ASR archive. This is a DOE program that has been going on for a few decades. And they're very well distributed around the world. So we have these episodic but very long-term observations of this variable. Problem with this is that the experimental error could be significant, so we have to be very careful about how to use those. Also, as I mentioned before, the data is not particularly well suited for machine learning because it has all of these. Typically, if you look at, let's say, this site, you have a long-term observation, but it's also depending on the fact that you have clouds there, or maybe just on the boundary layer, and everything else is nuts. And also you have the reanalysis, of course, and that is useful to provide this true atmospheric state at each of the sites when we are training on them, and later for inference. So this is kind of a more detail, but still a little bit over, well, giving you an eagle view of this, what we're doing, of the process that we use to generate these estimates. So first, as I mentioned, we train a surrogate of this high resolution model using downscaling on the one side the state and on the side the vertical velocity field to find the standard deviation in vertical velocity. And then we refine their own sites. I'm gonna come back to this because this looks a lot more complex than I explained before, but there is a reason for it. And I'm gonna explain that later. And then once we have this, we can get just use the reanalysis to get our inference and our global estimate of sigma w, which is what we're interested in. Again, we at the end we're trying to get both the model that we use for that we can use later for parameterization, and also the product, which is what we provide to the community. So this is the first part. Can we train a model that is a surrogate of the global cloud resolving model? Yes, it's actually not that hard, and these neural networks are nothing special. Actually, for this particular problem, this was a few years ago, we use just an MLP. If you do it cell by cell, it's actually not a bad thing. You can train that to reproduce the GCRM pretty well. I mean, it takes a few hundred tries, but you eventually get it. So here, this is our prior distribution, and then our prior neural network, and this is our GCRM, which we call the GFI nature run, just for internal reasons. So we are able to reproduce that quite well. But then this is what happens. When you go to the site and you pick any particular site on that grid that I showed before, it tends to do this. It tends to underestimate the observations badly. Why? Because we have a 7-kilometer resolution model, which tends to miss a lot of the variability dynamics in the atmosphere. But still, we can still use that as a feature extractor, right? Something that will tell me, well, you should have high velocity here. You should have high velocity here, even if it is the magnitude is not correct, right? So let me step aside a little bit. So for the second part, the refinement part, we have to take into account error, as I mentioned before. So let me give you an idea of how we did that, because it's not something that turned out to be way more complex than we thought. So for that, let me introduce, get you back to the old GAN, the generative adversarial network from your machine learning 101. Probably you remember that these were the first, like in 2014 or so, the first actual generative AI like technology that was able to produce really good good pictures, good graphics. And the way they work is that they they pit one network against another, right? So you introduce a second network that will, let's say that it has a generator. In this case, the generator will be our prior, right? Our prior neural network. So this generator presents examples to the discriminator. The discriminator is learning directly from the data, right? So and it's a classifier essentially. So it tells it, based on its own representation of the data, it says, okay, whatever the generator produces is within the distribution, is within the manifold of things that I'm learning. So I say that example is real. Or it's outside of that manifold, then it's a fake. And then I penalize the generator. Eventually, they go together and they both learn the same distribution, which is the distribution of the actual data. Which is what we want, essentially. This is a very nice and cartoonish way to explain it. And well, something that I should mention is that if you actually you can condition this to essentially work for a particular state. For example, if you have the distribution of all human faces, you can condition these networks to just produce human faces with, blue eyes or something like that, which is good for us because then we can tell it just predict examples that are that agree with this particular state, right? This is well known. Probably you knew about this before, but what is not known is that or that is less known, is that this kind of setup can be also used to correct for experimental error. So we go back to this diagram that I had before, where we use our sites, the state our site and on our sites to generate on the prior to generate some estimate of that sigma w. And you actually follow this, you see that this guy, WNet, the generator, it never sees directly the data. Never. It always sees whatever the representation of the data the discriminator is learning. On the other hand, the discriminator cannot learn from noise. That's not what neural networks do. They just learn from structured data. So if they learn at all, they are learning something that is not noise. So that means that this guy is a filter. It only presents true data to the generator, in this case, WNet. So we can say that WNet is learning only from the clean up data, from the filter data. And that way we get rid of that experimental error that tends to be derail all of these efforts. Well, there is some, typically the WNet loss or these loss in the generator will be something like, some KL divergency between what the discriminator is learning and what the generator is producing. I just said that it is only experimental error, but it's not. So in reality, this discriminator and this setup will correct for everything in the generator in WNet that is not the observed manifold. So that also corrects for superior scale variability for whatever discrepancy we have. So we really don't have a way to discriminate what is experimental error from what is actually theoretical or uncertainty. But still, I mean, it works to train on the actual data, and that's what we do. So this is after applying that kind of scheme to this problem, this is what we end up with. So you look at this plot over here, and then you go back a couple of slides. This is the same plot. So of course, that works wonders. I mean, you get really close to the data using that particular approach. So using that observational data is critical for performance, and we learned that pretty quickly. But what we saw also is that, let's say that we take that initial step when we train on the simulations first, we take it out of the equation and we just train on the sites, on the actual ground-based observation that we have. And well, if we do that, then we end up with only with this kind of thing. And that's because this feature structure is very important. If we just use the sites, then the sites the neural network have no clue how to go about extrapolating or interpolating between the sites. So in places where you don't have that much coverage, tends to just assume that it's all the same because there is no way for it to know. So that part is what that initial simulation, although it was biased, is providing to the final product. Okay, and this is all just to emphasize that this network or this particular setup, when we use generative adversarial networks, is able to get the actual distribution of the data. So here are the statistics. This is our prior, and that prior, sorry, was of course biased, and then we were able, this generative approach is able to correct for that and get the right distribution, which is what you want for the parameterization. There is like this mantra in the parameterization development community that even if you, on a particular event, on a particular case, your parameterization has a large error, the important thing is that on average, you actually get the right distribution, that the error is not systematic. And that's what we get here. On the other hand, if we only have observation, you see that we really can match that observed distribution. Again, because there is no interpolate, there is no way for the network to extrapolate or interpolate even. So that's the neural network part on this. Gonna be in the next 3 slides. I'm gonna kind of step out and then talk about science a little bit, because once we have the product, there are cool things that we can do with it. So, well, the first thing that we did was using both MERA2 and MERA5, and this neural network that we developed, and with this refinement process, we throw that to the reanalysis, the whole data set, and then we had this long-term data set on sigma W for 42 years, and that is 3 hourly and a half degree, and it goes over the whole atmosphere. And there's something that we can provide. And it's actually, well, I didn't put the URL here, but that's something that is open. If you want to go and download it, you can download that. Familiar patterns, you can see there is high variability here. This sigma W is related to turbulence, and you probably know that already. You see that these orographic regions, they tend to have these high vertical velocities and this high variability in vertical velocity, as you have said. And well, you see storm tracks, you see things that are very, very interesting. Jet stream, probably you can even, put a little bit over there. But then we got this 3D data set, that is very quite dense, at least for a GCM. The next thing that we have to do, of course, was to validate this. We cannot just trust our own data, and we cannot just trust our own process to say that we have a good product. So the next thing is that we did was we got in touch with Hugh Diao at San Francisco State University, and what they have done is collecting this, and here students, they collected a lot of sigma W values of these observations from different field campaigns that have happened over the last probably 10, 20 years. And you can see that here, all the trajectories. And what we did was map, or essentially collocate those curtains on our data set, essentially fly those planes inside our data sets and see how things look like. And this is for all of the, this is blue here. Well, if you just use MERA2 to drive, ERA5 to drive, you actually do one of them, which tends to do better, and this is the observations. And we were actually pleasantly surprised because this is a very rigorous test. We didn't use any aircraft observations or any of that in our development. Yet the network is able to predict that. And this is even a different technique. The other one was radar. These are actual measurements done with a probe in a plane. We don't do well all the time. For example, if you look at this Atrix here or this Poseidon, well, we actually are kind of overestimating variability there. And if you actually go ahead and look where those happen, well, that happens where we don't have enough data, which tends to be a problem with this. So we are always looking for more data to refine these networks. And the next thing that, well, then since we trust this data a lot more now because we validated it, then we can go and we went and look for trends. And we found that, almost everywhere, this sigma W variable is been increasing as told by the reanalysis. And there is a significant trend, at least that we have found in the last 40 years. This means that there is that the atmosphere is becoming more turbulent, and because it's more turbulent, then it tends to enhance that cloud formation event. So that means that you have more droplets, and those more droplets, if you keep the liquid water path or the water vapor constant, they tend to produce smaller, more and smaller droplets, and then that will increase their thickness. So they're becoming more opaque. And this, we did a lot of analysis with Shapley and other things, and we can actually attribute this to changes in water vapor and temperature. So what I'm trying to say here is that the long-term climate change is also changing the smaller scale, and that is getting a feedback into climate. So it goes both ways. Not only the aerosol and all of that is changing climate, also the climate is getting back to it. We went back all the way to the 1900s using a theory analysis, in this case, era 26. And what we found is that, well, that's actually quite significant. There's been a generalized increase in sigma W over the whole globe. and that translates essentially into a minus 0.1 watts per square meter cooling that is being put as as an offset, let's say, of global warming. And that's still pretty small with it. The 14 by CO2 is about 2 watts per square meter, probably around there. So it's still small, but it's something that is probably adding uncertainty to our estimates, and it's probably going to change in the future. So in the next 10 minutes, probably less than that, I'm going to just give you new data. This is not new data, but I'm going to talk about the new project that we have been working on over the last year, trying to apply this methodology to another variable, which is the cloud droplet number concentration. So what do we care about the cloud droplet number concentration? Well, we know that, and I'm going to call it ND, determines to a large extent the evolution of clouds, and it's very important to understand the effects of pollution on clouds and climate. And many people know that. That's why we care so much about aerosol cloud interactions. Tapio Schneider, he was talking yesterday about that, how important that is to get right climate predictions. And well, this is from our recent reanalysis called GI Ocean. I'm going to talk about that in the next slide. But you see that there is a they are essentially anti-correlated. The cloud droplet size, which is this area effective radius, and the droplet number concentration. They pretty much match each other. This is like 0.8 anti-correlation, minus 0.8 correlation between those two. Current estimates are derived from MODIS, using either optical depth, liquid path, effective size, things like that. We will argue that to be able to derive that directly, you have to introduce strong assumptions about how the cloud field looks like, the cloud structure, and how things evolve. And also because MODIS is essentially a radiometer, that is flying around on the top of the atmosphere, then it provides only a 2D view of clouds, and we know that clouds are 3D. So what data? See, we want to tackle this problem. What data we have? Well, as I mentioned, we have our new GI ocean reanalysis, which is a coupled atmospheric ocean aerosol reanalysis that has two-moment microphysics. So it has explicit aerosol cloud interactions, and it's one of actually the first of the kind that has that kind of physics. Probably not gonna last longer at the first of the kind, because I just read yesterday that ERA 6 is coming with aerosol cloud interactions. So we enjoy our top spot for now, probably a few weeks. The nice thing also is that when we develop this simulator, this reanalysis, we run a MODIS simulator, which is it's called COSPI. It's developed by, I think, I can't remember. I think it's Caltech. And essentially, because we have those two pairs, the simulated retrieval and the ND, then we can train on those pairs and try to get that first estimate. Itself, the reanalysis is not that bad. If we take all of the assumptions that are done in the MODIS retrieval and then we just put together something, well, it doesn't look too bad. Actually, it's very close. So that we're gonna take advantage of, because that simplifies things a little bit. Observational data, ND can be derived using radar and microwave radiometers, and mostly in this CloudNet archive, we found that these are around 34 sites, mostly in Europe, and the data looks just as stressful as the other one. And combined, well, of course, we have the long-term MODIS retrieval. I'm gonna kind of speed up a little bit because I'm about to get run out of time. One thing that I'm going to emphasize here is that we want to take 2D data and then get a 3D variable. And that usually implies that we have to do some 3D convolutions, which I completely hate, because those are very hard things to do, and they tend to blow up your memory, essentially. So, but as I mentioned, we can take advantage of the GI Ocean data set by doing Fourier or DIF decomposition, in which we compute the anomaly using our prior data set, and then we can decompose these two things, the anomaly between the pre-compute empirical orthogonal functions of the principal components, and then restrict our problem to just predict these 2D coefficients for each of them. And that it reduces the dimensionality of this problem, so we just have to go from R2 to R2 instead of trying to get these 3D convolutions. And that's what we did. This is essentially an image translation problem, right? And that essentially suggests that we probably can use a unit for this, which is exactly what we did. So we have these simulated model variables. Then we train a unit using MSC as a loss. And well, this I should mention, we cannot get rid of the whole 3D data set really, but we can use it in this way just only in the loss. So during the loss, we reconstruct ND, and then we can get that a better constraint. So after we get this coefficient, then we can go back and invert that equation that I showed before and get the actual ND and get this. Our estimate, our surrogate. And that's essentially, that's not a bad, well, it again, takes a few hundred tries, but then eventually you get it. And then we can do that pretty well, probably, some biases, but we are not interested in getting the surrogate perfect. We're interested in getting the right physics first, right? So the next part, of course, is how we go about and correct this. And in this case, what we did was not trying to get this like putting an additional layer onto the prior as we did with WNet. We actually got two different neural networks. And the reason why we did that is that we need to be able to anchor that first estimate or the second neural network, that correction head. We need to be able to anchor it to the prior. Otherwise, it just goes crazy and then it starts to increase things where they have where the data is more available. So for the loss here, we have a Gaussian NL, and that's also nice. The other reason why we included this correction head separately is because we are also interested in some envelope of uncertainty that is predicted by the network, and that is a different output that we will have with this only. So again, in the reconstruction, and that NNL space essentially is a Gaussian loss plus some anchor. That's how we train this thing. So what it did is what you will expect it to do, right? So here I'm showing on average across all sides the vertical profile of ND. Well, yes. So this is our prior. Well, this is the data that we had before. GI Ocean that we thought it was great, but actually it tends to underestimate at the surface. Especially, it doesn't have the right vertical profile. This is that surrogate prior, just driven by modis that we can do that, but it still is based only on the prior, only on the GI Ocean data set. And then this is our refined product that is much closer to the observations. We do tend to underestimate the variability quite a bit. So we don't know, this could be a product of our augmentation, that augmentation that we just actually copy things many times. We just copy the same thing many times without adding variability. It tends to narrow things up a lot. But then, the next question is, okay, so this is on the sides, but what does it do globally? Well, one thing about this neural network is that we're never fitting the state on the side. We always fit global, and then we interpolate on the side because we are interested in a global product, right? So this is our prior. You see there is some differences there, but still it conserves all that physics from before. We have all this where things are supposed to be high when they are supposed to be low, and then it's just a correction that it adds to it. We are still at this point, we don't know how much of the correction, how much of the anchor we should allow, how much of the side we should allow. And right now we're just doing 50-50 just because it is now. We don't have a better answer for it. And the nice thing is that we can also get an envelope of uncertainty that in the standard deviation is now predicted directly from the model. We didn't try to do generative corrections here because we don't think the data is good enough to do that, and it will just go back in circles trying to train that gun. So for that, I think that I just wanna read my key takeaways here. We think that through simple machine learning techniques, simple in the sense that we're not using transformers or we're not using, LLMs or anything like that. It is possible to integrate satellite retrievals in Situ observations and modeling into a new type of product. This works better for derived variables for which a theory is already established, so at least that we have some theoretical way to understand this. And we are actually, now we have a hammer. We're looking for all kinds of nails to try to hammer on. And so we actually have a project going on with this, try to model cloud fraction. But we're also looking at phase partitioning, aerosol cell distribution, ice crystal concentration, convective displacement. And you have any ideas, what else this can be useful, just let me know. Thank you very much.